Hello everyone. Today we shall discuss electrocyclic reactions, and these are the things which are there in your syllabus. From our previous classes, let us recall, if you have one pi bond, the number of pi electrons will be 2, and in thermal state the HOMO will be symmetric. When it comes to photochemical state, one electron will be promoted, hence the HOMO becomes asymmetric. Similarly, we can make a list like this. If you have 2 bonds, 3 bonds, 4 bonds, correspondingly with 4, 6 and 8 electrons each, the HOMO becomes symmetric, asymmetric, symmetric and asymmetric. So it is alternative. If you just remember one, you can find out the others. Okay, you should remember that for one bond, 2 pi electrons, the HOMO becomes symmetric. Let us look at this example. 2E, 4Z, 6E octatriene. You should be familiar with this E and Z notation. I have already discussed it in your class. Yet once again, let us recall. E means opposite. Z means together. Okay. So the first priority on the opposite side gives you E configuration. The first priority on the same side gives you Z configuration. So here it is 2E. So first priority CH3 and this molecule which is on opposite side, therefore E. Here 6E, again first priority on opposite side, therefore it is E. It is a triene because it has 3 double bonds. When it has 3 double bonds, you have 6 pi electrons. Recall from the previous table, 6 pi electrons, HOMO becomes symmetric under thermal state. If you do the same in photochemical state, HOMO becomes asymmetric. Look at this flow chart. So this is octatriene. Under thermal state, symmetric, hence the lobes of similar kinds are on same side. Okay. Under photochemical state, the lobes become opposite. Correspondingly, you have E configuration, therefore CH3s are on the opposite side. Whereas here, under thermal state, you have symmetric in Z configuration, 6Z, and under photochemical state, you will have them on the opposite sides. Okay, the only difference is CH3 on the opposite sides and CH3 on the same sides, because this is Z configuration, this is E configuration. Let us look at another example where you have 2 double bonds. The number of pi electrons are 4. Hence, the thermal state HOMO becomes asymmetric. Here you have thermal state HOMO asymmetric. Under photochemical state, it becomes symmetric like this. So you have 2E4Z hexadiene, Z which means together, therefore CH3 have been drawn together. Here it is hexadiene 4E, which means CH3 are on opposite sides. Okay, but under thermal states, you have asymmetric HOMO. Under photochemical state, you have symmetric HOMO. We are dealing with electrocyclic reaction, which means the pi bonds are going to rearrange. One pi bond is going to be utilized in getting converted into a sigma bond, right? So you have 2 pi bonds here in hexadiene, which means one pi bond will be formed between this carbon and this carbon, and this pi bond is going to get rearranged. It's going to get rearranged. So when the sigma bond is going to get formed, there should be overlap of orbitals. That is what we are seeing here. How the overlap is going to get influenced under thermal condition and under photochemical condition. Let us consider 2E4Z hexadiene. I told you Z means CH3 are together. We have written them together here. And under thermal condition, HOMO is asymmetric. When you have an asymmetric HOMO, Just check. We are supposed to rotate this lobe clockwise. Okay, this lobe clockwise and this lobe anti-clockwise. This lobe also clockwise, sorry. This lobe clockwise, this lobe also clockwise. Then these two lobes can confront each other, forming a sigma bond. Okay. When you are going to rotate both the lobes in the same direction, we call that rotation as conrotatory. If you rotate the lobes in opposite direction like this here, see, one in this and the other one in this direction, we call that rotation as disrotatory. Okay, I repeat, 2E4Z hexadiene under thermal state, HOMO is asymmetric. In order to form a bond, both the lobes have to rotate themselves in clockwise direction. Such rotation is called as conrotatory. Okay, while conrotation occurs, see here, while you rotate this down, CH3 comes down here. CH3 will come down. When you rotate this also in clockwise direction, CH3 is going to come down here. So you have two CH3s here below on the same side of the plane. Hence you get a cis product. Cis 3,4-dimethyl cyclobutene. This is an electrocyclic reaction where 2 pi bonds is converted into 1 pi bond and 1 pi bond is converted into a sigma bond. Okay, let us consider this under photochemical condition. You have to rotate the lobes in opposite direction, which is disrotatory, giving rise to trans 3,4-dimethyl cyclobutene. Okay, see, while you push this side, CH3 comes down. While you push this in the opposite direction, CH3 is going to go up. So 4Z configuration will give us cis product in thermal state. 4Z configuration under photochemical state will give us a trans product. Such reactions are known as stereospecific. So you know what kind of product you are going to get under a specific condition. Okay, now let us look at this 4E, 2E4E hexadiene. The lobes are similar, asymmetric and symmetric here. Well, you have asymmetric, you're going to rotate both the lobes in the same direction, hence it is conrotation. But in this case you're going to get a trans product. Whereas here you're going to rotate both the lobes in opposite direction, hence here you're going to get a cis product. Now let us look at 2E4Z 6E octatriene. Fine. See here, we know under thermal state HOMO is symmetric. So symmetry, you have to do disrotation. Symmetric HOMO, disrotation. So while you do disrotation, CH3 is pushed up, CH3 is pushed up. Obviously you're going to get cis product. Whereas under photochemical condition, HOMO is asymmetric. You're going to push one CH3 up, the other CH3 is going to be pushed down. Both the lobes are going to be rotated in clockwise direction. Therefore, it is called conrotation, and the product you're going to get is trans. So this one is about 2E4Z 6E octatriene. How about 2E4Z 6Z octatriene? So 6Z, CH3 are on the same side. So under thermal condition, once again, you have symmetric HOMO. You have to do disrotation, you'll get trans product. Whereas in thermal state, you have to do conrotation and you're going to get a cis product. Now you're supposed to write the Woodward and Hoffmann selection rules for all kinds of electrocyclic reactions. All. So see here, when the number of conjugated bonds are odd, when it is odd, the ground state or thermal state HOMO will be symmetric. Okay. When the number of conjugated bonds are even, the ground state or thermal state HOMO is asymmetric. We have seen both the examples. So we have seen diene and triene. Okay, we have seen diene and triene. So you have to see number of conjugated bonds if they are odd or even. If the reaction condition is thermal, the allowed mode of ring closure will be disrotatory. If the reaction condition is photochemical, the allowed mode is conrotatory. Okay, so you can easily understand if the number of conjugated bonds is odd, HOMO becomes symmetric under thermal condition. When you have symmetric, we know it is disrotation. Okay, under thermal condition. So thermal condition conrotation is forbidden. What is allowed? Only disrotation. Under photochemical condition, automatically HOMO becomes asymmetric. When you have asymmetry, there is conrotation. Right? Therefore, disrotation becomes not allowed, forbidden. It is forbidden. Okay? In even number of bonds, the HOMO in thermal state or ground state is asymmetric. Asymmetric means conrotation. Photochemical, it becomes symmetric. Therefore, you have disrotation. So these are the Woodward and Hoffmann selection rules for electrocyclic reactions. So quickly let us go through what we have seen in this particular session. We have recalled that if the number of pi bonds is 1, you have 2 pi electrons, HOMO becomes symmetric. So this is odd. When you have odd number of pi bonds, HOMO is symmetric. When you have even number of pi bonds, HOMO is asymmetric. Okay. So based on that, we have seen how we are supposed to draw the lobes, symmetric lobes and asymmetric lobes. We have to consider the configuration, that is either it is a 6Z or 6E. And then we have seen two examples, hexadiene and hexatriene, trienes and dienes. Okay, and then we have seen conrotation and disrotation in both the cases and arrived at Woodward Hoffmann selection rule for electrocyclic reactions. Thank you.